Let's review torque. Now, torque is a lot like force in that torque's the thing that causes the accelerations when you're rotating, in the same way that force is the thing that causes the linear or translational accelerations. And just a little bit of bookkeeping, the symbol we use for it is this one, sort of a squashed little T. That is a Greek tau. The units are newtons meters. And I just want to stop right there because previously when we met them in energy, newtons times meters were joules. And that's not the case here. For the first part, torque is a vector and joules was for energy, and energy was a scalar. So that's very different. But the other thing that's going on here is, like a lot of rotational variables, there's a hidden radians in here. And there's a there's a meters, and so the radians disappear, they ghost out. But just keep in mind, even though it's newtons times meters, torque is not in joules. All right, so having got that out of the way, what do we do to find torque? Well, torque is given by the cross product of R, which is something called the moment arm, with the force that causes the torque. So let's just write down R is known as the moment arm, and it's the distance between the axis of rotation to where the force is applied. So it's a vector, it goes from the axis of rotation, AOR, that's the axis of rotation, to where the force is applied on the object. So that means we're going to have to be paying attention to where we're drawing our forces and making sure we're drawing them in the right place. So let's just do an example. Here we've got an object, and let's say we've drawn it flat down so that the axis of the rotation is coming out of the page at us. So I will draw it as just a little circle there. This will be a top view, say. And if I do that, now I can go ahead and draw my force in. All right, so let's just say my force kind of goes off like this. There's the force that's applied to this. And we'll also draw a side view, just so we can get a better idea of what's going on. So first we'll draw the axis rotation, which, remember, that's like the hinge or the axle or the pivot or whatever it is this thing is going to rotate around. So we could draw it as just like a column like this, something that maybe there's a hole in the object right there. So it fits around this column, so then it can rotate around it. So this is the axis of rotation. And then if we draw our object, now we're looking at it from the side, so it'll be kind of a squashed thing like this. Maybe it has a little bit of depth like this. So it's kind of, I don't know, maybe a slab or something. And then the axis of rotation, it travels through the slab. We can't see it because, of course, the object's in the way, but then it comes out down here. And then our force, so I'll need to go get my other color again. The force is sort of applied here, and it goes off into the back of the paper like that. All right, so here's our object and the force. Now we can draw the moment arm on there. But I guess first let's just go ahead and give this force a magnitude. Let's say it's 15 newtons. Okay, so the moment arm, it goes from the axis of rotation to where the force is applied. So here's the axis of rotation, it starts there, and it goes to where the force is applied. So the moment arm is gonna look like this. And let's say the force is applied 2 meters away from the axis of rotation. And then on our side view, it's going to go from the axis of rotation to where the force is applied. There we go, that's our there. And then the last thing we need, because this is a cross product, we need to know the angle between them. So remember, if you're finding the magnitude of a cross product, in this case it would be the magnitude of the torque. That's the magnitude of the two vectors they use to create their cross product, and then the sine of the angle in between them. So that's the angle between the moment arm and the force. And this is really the difference in their directions. So where is that angle? Well, it's very tempting to say it's this angle here, but it isn't, because this angle is the difference between their directions. So what we really need to do is kind of, mentally extend out what the radius or the moment arm is doing here. And it's this angle like that. And a clearer way to do this, to show this, is to actually redraw these two vectors so they're starting from the same point. So I'm going to do that off to the side. Here's my moment arm. And there's my force. And now when I've drawn them as if they're starting from the same point, then it's relatively easy to see the difference in the directions. It's going to be this angle here, and let's just go ahead and call that 30 degrees, just so we've got a number. Okay, so now we've got all the ingredients that we need to find the magnitude of the torque here. It's going to be the magnitude of the moment arm, which is kind of like the radius. That's where those ghost radian units are coming in here, but it's 2 meters. That's how we actually write it. The force, it's 15 newtons. And then the sine of the angle between them, or the difference in the directions, that's 30 degrees. Okay, so 2 meters times 15 newtons, that is 30 newtons meters. Sine of 30 degrees, that's 1/2. So the magnitude of this torque is 15 Newton meters. And again, because it's torque, it's a vector, it's not an energy, we don't convert that Newton meters into joules. We just leave it as it is. Okay, how do we find the direction? Well, it's a cross product, so we use the right hand rule. So we take our right hand and we point our fingers in the direction of the first vector. That's the direction of the moment arm. Then we rotate our hand so we can then curl our fingers towards the direction of force, and our thumb will point in the direction of the result in torque. So looking at this, we have our moment arm points out like that, our force points out like that, or we could do it here where both the moment arm and the force are starting from the same location. And what we would get is this would be here, this would be out of the page. So let's go ahead and draw that. So here on our top view, that torque would be out of the page. So we would use the out of the page symbol there. There's torque. You get a little shade so you can see that. And then here on the side view, the torque would actually be coming like this. It would go up the axis of rotation, which is generally what happens here when you're dealing with rotation. So the torque goes up the axis of rotation like this, and that makes sense, just kind of considering the original purpose of torque, which is it's the thing that causes accelerations. So if this object were stopped, and that were the only force applied to it, and so this here were the only torque, what is this force going to cause this object to do? How is it going to cause it to rotate? So the torque's like this. If the force is pointed like this, well, and this object is stopped, we're going to expect this object to start rotating around like this. And that is an acceleration that is up, in other words, in the same direction as torque. So I'm going to remind you of Newton's second law for rotation. That is the net torque, the combined effects of all the torque acting on an object, is equal to the moment of inertia times the acceleration of the object. So the direction of the net torque is going to be the same as the direction of the acceleration, and that's what we're seeing here with our direction of torque. And if this is the only torque acting on it, it's going to cause this thing to be accelerating around like this. So there you go. That is a quick summary of torque.